Hello, good morning everyone. We are going to start the last part, almost the last part of volumetric analysis. Therefore, I have given this chapter, this part as Kilimanjaro trekking starts. Because whatever knowledge we have acquired in the equivalent concept V1N1 is equal to V2N2, we shall be utilizing them in solving analytical problem, analysis of a sample involving successive reactions and back titration. We shall learn what is back titration. So all our experiences so far will be applied here, and we shall summit the Mount Kilimanjaro. I used to funnily say that this is the Kilimanjaro trekking, the highest mountain peak in Africa, which is situated in Tanzania. As you know, Kilimanjaro. A lot of people every year, every good season, they are summiting on the mountain top. And just for fun, I used to say, let's summit on the Kilimanjaro of volumetric analysis, part 5. Let's start. Now, what is back titration? How to analyze a sample? And let me read out, just focus on my words. A sample to be analyzed is allowed to react with excess of the reagent having a known concentration. For example, you have a sample of calcium carbonate, an impure sample, right? You treat it with excess of sulfuric acid having known concentration, normality, and the volume that you add is also known to you. So the reaction is complete. The sample, the pure substance present in the sample is the limiting reactant. It completely is exhausted. And after the reaction is over, see here, the excess amount of the reagent is estimated by titrating the solution with another standard solution. You know what is a standard solution. I remind you, if the concentration of the solution is accurately known, then that's a standard solution. And to know how much of the reagent has remained in excess, we have to perform a titration experiment. This is called the back titration. Back titration means we are getting the knowledge of how much reagent is kept or is left in excess. We have to titrate at the end. So that's why it is back titration, which is done at the end. We determine the amount of the reagent consumed in the original reaction from the back titration data. Once we know the amount of reagent left out, then we know what is the amount of reagent originally taken. And subtracting from that, we get the amount of the reagent consumed by the original compound present in the sample. Sometimes before titration, dilution is done to bring the concentration of the unreacted excess reagent, unreacted reagent, comparable with the titrant concentration. Because you will be using a titrant to estimate the amount of the excess reagent. So to have a matching of the concentrations, as you know, the concentration of the analyte and the titrant should be comparable, should not have a large disparity in their concentrations. Then only you get a reliable result. And after you do that, you know what is the amount of or the milliequivalents. You go by the equivalent concept, number of milliequivalents or equivalents of the reagent used. You will also say the same number of equivalents of the original compound in the sample. So you can convert to the mass. If you know its identity, and know the n factor, you can convert to its mass, and then you find the percentage of purity in the sample. Let's take an example. See, this is a sketch, the schematic representation. The sample is an impure sample, right? Excess reagent whose concentration is known, whose volume is known, and after the reaction is over, the unreacted reagent is determined, is estimated by titration experiments. This is called the back titration. For example, you have impure calcium carbonate, you add excess sulfuric acid, and that too, you know the volume and you know the concentration, 200 ml of N/2 sulfuric acid. Reaction is over. Then the unreacted sulfuric acid now is titrated either directly or after dilution. Say directly, the titration with a standard base, right? Then you know from this back titration, you know the amount of excess acid, and by subtracting, you know already what is the amount of the original acid taken before the reaction. So subtracting this from this, you get the amount of acid consumed by calcium carbonate or copper carbonate, whatever. Then, as you know, the chemical reactions take place in equivalence, so the number of equivalents of sulfuric acid is same as the number of equivalents of calcium carbonate. So then you can convert to its mass and then find the percentage of purity. Clear? Now let's take an example. 0.21 gram of a metal is treated, it's a metal, as an impure metal. I'm sorry, it's a pure metal. 0.21 gram of a metal is treated with 200 ml of 0.25 N sulfuric acid, and the metal dissolved completely. It means that this is the reagent taken in excess, deliberately. Now the residual acid after the reaction with the metal required the back titration. 65 ml of N/2 caustic soda solution for complete neutralization. Calculate the equivalent mass of the metal. Now you start solving such problems from the backward direction, from backward to frontward. You understand? So from the back titration, you start your journey. So 65 into 1/2, V1 into N1, 65 into 1/2. It is the number of milliequivalents, MEQs of NaOH consumed in the back titration. So the MEQ of the excess acid must be equal to the same. The MEQ of excess acid present in the entire solution, entire 200 ml solution, the MEQ, milliequivalents of excess acid, must be same as much caustic soda, NaOH is consumed. As much NaOH is consumed, same will be the MEQ of the excess acid present in the 200 ml solution. Then we find out what is the original milliequivalents of acid taken. 200 into 0.25 is 50. So 50 was taken, and out of which 32.5 has remained in excess. That was determined by back titration experiment, and you subtract this from this, you get the MEQ of the sulfuric acid that has been consumed by the metal. Metal identity is not known. Its equivalent mass, supposing, is X. Right? Now see. Hence, the milliequivalent of the metal is also 17.5, because all chemical reactions take place in equivalence. If the milliequivalence of sulfuric acid consumed by the metal is 17.5, then the milliequivalence of metal is also 17.5. But here there is a problem. It is because the N factor of sulfuric acid is 2 in both the reactions. You see, the back titration is an acid-based titration. It's a non-redox metathesis reaction, right? But the first reaction, the reaction of metal with sulfuric acid, is a redox reaction. It's not a metathesis reaction. But sulfuric acid is the common reactant. I mean, zinc reacts with sulfuric acid, and that excess sulfuric acid reacts with NaOH, right? So, since sulfuric acid here acts as an oxidant in this reaction, and the total change in oxidation number is also 2, H2SO4, hydrogen goes from +1 to 0, and there are 2 hydrogen atoms, so total change is 2. So, luckily, we can climb the ladder of in the hierarchy, in the successive reaction hierarchy to the top by equivalent method. It is, in this case, is correct, but not in all cases. I told you, I cautioned you, you only adopt the V1 N1 is equal to V2 N2 technique only for a titration experiment. The moment you get the milliequivalence of a particular reagent, convert into millimoles by using the N factor. Divide the number of milliequivalents by the N factor to get the number of millimoles, and then climb the ladder through mole method. Balance the equation and then correlate between the two species. But here you can justify to climb the ladder in equivalent concept. So you see here 17.5 is the number of milliequivalents of the metal, and let's say the equivalent mass of the metal is X. So 17.5 and you kill milli divided by 1000 into the equivalent mass, that is equal to the amount of the metal given, 0.21. So by solving we get X is equal to 12. So the equivalent mass of the unknown metal is 12. Obviously it has to be magnesium. Very presumably it is magnesium, because magnesium, the atomic mass is 24 and its N factor, valency factor, is 2, so it is 12. Forget about it. Now let's look into the real logic. Supposing we will solve this problem in mole method. First, the titration, well, yes, V1 N1 is equal to V2 N2. So we did that. The equivalent concept was applied to the back titration. We got the MEQ of excess acid this, and the millimoles immediately we converted into millimoles, because we have to climb the ladder in mole concept, mole method. So the number of millimoles of the excess acid is 32.5 divided by 2. Because this is an acid-base reaction, the basicity is 2, the N factor is 2. So 16.25, since the N factor is 2 here in the acid-base reaction, so 16.25 is the millimoles of excess acid. So you converted milliequivalents to millimoles, and the millimoles of sulfuric acid initially taken is 200 into same, because the normality is given here. So the N factor of sulfuric acid in this reaction also, zinc plus sulfuric acid in that reaction also is 2, so the N factor is 2. So 0.25 divided by 2 is the molarity. I mean, so you get the N factor is 2. Now the number of millimoles initially taken is 200 into molarity, 0.25 by 2, that becomes 25. So 25 millimoles of sulfuric acid initially taken, out of which 16.25 has remained in excess. So you get the number of millimoles that has been consumed by the metal is 8.75, right? Then you write the equation. You do not know the valency of the metal, so you balance this in terms of X. So it comes to be 2m plus X S2SO4 gives M2SO4 whole X, because sulfate has valency 2 but metal has valency X, plus XH2. Now from the stoichiometry, X millimoles reacts with 2 millimoles. So 8.75 millimoles will react with 2 by X into 8.75 millimoles, right? Then the mass of the metal is given 0.21 is equal to number of millimoles 2 by X into 8.75 kilmilli divided by 1000 into atomic mass. Since it is you are taking mole here, 1 molar mass is the gram atomic mass, and here we have to apply a trick, because atomic mass is equivalent mass into valency. So instead of atomic mass, we write equivalent mass into valency. So this valency factor gets cancelled and you get equivalent mass straight away equal to 12. You understood the logic. Same answer you got, but here you solved through mole method, and there in the earlier case you solved by equivalent method. I am spending time to solve in 2 methods because I have cautioned you, and I am cautioning you now again and again that in analysis you will encounter with a very, very long analysis with multiple successive reactions, parallel reactions, and you don't be scared. Often students get scared to look into such a huge voluminous numerical, starting from the top of a page ending at the bottom. They are scared. Now I'm sure if you have a little time, then you just love it to make a sketch. Read carefully and make a sketch what is happening, how it goes till the end, the back titration as the end, how it happens. So make a sketch putting the data, and then it will become easier on your part to go for a calculation, and you will find you will love to solve such analytical problems, volumetric analytical problems, very, very passionately, right? So never ever think of climbing the ladder throughout by equivalent method. Yes, if all the reactions are metathesis, non-redox, yes, the valency factor of any species won't change at all, because no oxidation, no reduction, so valency factor will remain same. So you can, in that case, can climb the entire ladder to the top, from bottom to top, by equivalent concept. But if you are involving a redox, then metathesis, then redox, metathesis, in a very, very heterogeneous manner, not in homogeneous way, you are involving the same n factor, but there can be a different n factor, same substance but experiencing different n factor. So don't run a risk, because you don't know, you might skip, you might not visualize that the n factors are not same and commit a mistake. So it is the best way to only apply the equivalent concept during titration experiment and climb the rest of the ladder to the top by molar method, by writing the equation and balancing them, right? Now let us proceed. I have already told you this. Note that in this case the first reaction is a redox reaction and the second one is a metathesis. Fortunately, n factor of sulfuric acid is same in both reactions, that is 2. So we could climb the ladder in the reaction sequence to the top by equivalence. This may not be the case always. Therefore, always apply equivalent concept only to the titration data and then climb the ladder by mole method, that is balanced equation or POAC concept. This will always result correct analysis. But in the case where all reactions involved in the sequence are metathesis or non-redox, then equivalent concepts should be applied to all the steps in the calculation. That means from the back titration till the start, you climb the ladder on the basis of equivalence. Supposing the last one, say, is the son, then the previous one is the father, then its father, then its father, then its father from which it is prepared, then its father from which it is prepared. So you go to the great 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 grandfather in equivalence, no harm, and it is advisable if all the reactions are metathesis, right? So let's take an example here where all the reactions will be metathesis. Read with me. 0.5 gram of a sample of limestone, which is basically calcium carbonate, and the rest impurity. Calcium carbonate is dissolved in 50 ml of N by 10 HCl. After the reaction is complete, the excess acid required. Now this is the excess reactant, excess reagent, and whatever calcium carbonate is present in this 0.5 gram, that's the limiting reactant. So after the reaction is complete, the excess acid required, this is back titration, the excess acid required 10 ml of 0.09 N caustic soda for complete neutralization. Find the percentage of purity in the sample. Since all reactions are metathesis, then let's start from back titration. Now 10 into 0.09 is the milliequivalence of excess acid, because that is the milliequivalent of NaOH consumed. So that must be equal to the milliequivalence of excess acid. Now the milliequivalence of acid initially taken is 15 to 1 by 10, that is 5. So 5 was initially taken and 0.9 has remained in excess, that you could estimate by a back titration experiment. Then what is the amount of acid consumed in the original reaction? That is 5 minus 0.9, 4.1. So the number of milliequivalents of calcium carbonate is also the same. As much milliequivalents of HCl is consumed, or in fact any reactant is consumed, maybe sulfuric acid, whatever, same is the number of milliequivalents of the original compound calcium carbonate. So now convert to the mass. The mass of calcium carbonate is 4.1 kilomilli into 10 to the power minus 3 into equivalent mass of calcium carbonate is 50. The N factor is 2, as you know, 50. So it is coming 0.205, and the percentage of purity is 0.205 by 0.5 is impure sample mass into 100. It's nearly 41% pure, and the rest impurity. But one thing, let us be very, very pragmatic, practical in our approach. Here we presume that the impurities are present in larger quantity. Say 59% is impurity. That does not react with acid. That the 59% of the impurity does not consume any acid. If that is so, if the impurity also reacts with sulfuric acid, then whatever back titration we have and we get the amount of acid consumed by calcium carbonate, it's not only by calcium carbonate, by the impurities also. So that will not give you the amount of calcium carbonate. So here we have the presumption that the impurities do not react with the reagent used for analyzing the main component of the sample. Now, this is similar. This is similar. Limestone, this is also limestone, but only different is dilution. Before back titration, the solution was diluted, because I told you what is the need of dilution. The need of dilution is to make the concentration of the excess reagent solution comparable with the other titrant that you are going, not other, the titrant that you are going to take to back titrate the amount of excess reagent. That's why sometimes it is needed to dilute. I told you, when you take, supposing in this case 0.2 gram of limestone was dissolved in 25 ml of N by 10 HCl. So calcium carbonate is all gone. The excess HCl is now diluted to 100 ml. That means you have added approximately 75 ml water, and to make the entire volume 100 ml with the help of distilled water. And then this is the stock solution. And take 2 times, 3 times. And also the reason of dilution is to get a sufficient quantity of the stock solution, so that you perform the titration multiple times until you get 3 identical values. That's the reason why sometimes if the original reactant solution, the volume is not much, then it is diluted. So there are 2 reasons for dilution. One, to get a greater volume of the stock solution, from which you can take multiple times in a pipette and perform the titration. And second, to tally, to have a comparable concentration with the titrant that you will be taking to titrate. Now the entire solution was made up to 100 ml. Then from that 25 ml of this diluted solution required 5 ml of N by 50. Can you imagine such a dilute solution? N by 50 NaOH solution for complete neutralization. Calculate the percentage of calcium carbonate in the limestone. Now let us start from the back side, from the bottom. Let's go for a back titration. V1N1 is equal to V2N2. 25 into X. X is the concentration, normality of the unreacted acid solution that is present in 100 ml stock. So 25 into X is equal to 5 into 1 by 50. So we get X is equal to 0.004 N. That's not the normality of only 25 ml. That's the normality of the entire stock solution, 100 ml. I think I did give you an analogy. The bitterness or the salty character of seawater is same to the tongue if you lick seawater inside ocean, you swim in the ocean and lick some water, seawater. As much salty to taste you experience, same experience you will be getting if you carry a bottle of seawater to your home and just put a drop of seawater on your tongue at your home. The salty character will remain the same. So the entire 100 ml solution has the same normality. Then you use this volume of the original stock solution 100 into the normality, that will give you the number of milliequivalents of the excess acid. You know, milliequivalents, millimoles, equivalents, moles, they are amounts. So by converting to milliequivalents or equivalents or moles or millimoles, we have rejected the use of any volume. Volume is no more present. We get the absolute, amount. So the milliequivalent of excess acid is 0.4, but the milliequivalent of acid initially taken before reaction is 25 into 1 by 10 is 2.5. So subtracting this from this, you get the milliequivalent of acid used by calcium carbonate. So that we have done. Milliequivalent of acid consumed by calcium carbonate is 2.1. So the milliequivalence of calcium carbonate is also same, 2.1. And mass of calcium carbonate is 2.1, and we kill milli by dividing 1000 into the equivalent mass of calcium carbonate, 50. It's coming 0.105. So the percentage of purity is 0.105 by 0.2 into 100, 52.5%. Got it? So the two numericals that we solved, they are similar. The only difference in the second case is dilution before titration. So you can also do it in a unitary method. If instead of doing V1N1, V2N2, supposing someone says that what is the milliequivalent of sodium hydroxide used consumed in the back titration, 5 into 1 by 50. So that amount of milliequivalent of excess acid is present in 25 ml. If 25 ml contains this much of excess acid, then 100 ml contains how much of excess acid? Same thing. Some students they solve in this manner. You can do that. You adopt any technique that suits you, that strikes to your mind first. Doesn't matter. If the logic is correct, then the way you solve is your prerogative, right? So the same, then you proceed in the same way. But this part is different. There V1N1 is equal to V2N2. We get the normality of the stock solution. Your intention is to find the normality of the stock solution, but you did not use the entire stock because you will be performing titration experiment multiple times. So you prepare a stock, take time to time 25 ml according to the pipette size available in your lab, and then find the titer value correctly. That V1N1, V2N2, that normality is the normality of the entire stock. But here what we did, we just simply find out the number of milliequivalents of the titrant in the back titration. Same is the milliequivalent of excess acid, unreacted acid present in 25 ml. If 25 ml contains this, then 100 ml, the stock solution contains how much? Some students, they can't conceive that if the normality of 25 ml is this, how can the normality of 100 ml will be that? So therefore they opt this method. You understood? But the same stock, same seawater, you are bringing 25 ml. So whatever normality or concentration that you get is the same with the entire stock. The entire stock contains our excess unreacted acid that we are going to determine, right? Now let's take this sample. This is a little bigger problem, but once you read it patiently, I'm sure you will develop great interest to solve it, right? Read with me. 1.6 gram of an impure sample of ammonium sulfate, again impure sample, was boiled with an excess caustic soda, NaOH. You know that any ammonium salt, when heated with any base, ammonia escapes. Ammonia is formed. The ammonia gas evolved was absorbed, but here we will not allow that to escape. We will take that ammonia via a delivery tube and bubble through and pass through 300 ml of N by 5 sulfuric acid solution. So again ammonia will be reacting with sulfuric acid to form ammonium sulfate, and the excess acid that remains is to be estimated, this time after dilution. The volume of this partially neutralized acid was made up to 500 ml. By using a 500 ml measuring flask, you transfer the entire contents so far into that and add distilled water and make up to the mark and sec it thoroughly. So it was diluted to 500 ml, and then 20 ml pipette was used each time. 20 ml of this solution required 15 ml of N by 10 solution of NaOH for complete neutralization. Find the percentage of purity in the sample. So what you are supposed to do after studying this question, my recommendations are first, you read the question 2 times slowly, then pick up a pen and draw the scheme. What is the events happening, sequence of events happening? Let me do that. Now the first we have to do, sketch out, this is the sample, the ammonium sulfate sample, and that is 1.6 gram. Then we added excess NaOH and heated. This volume is not required. We have not back titrate with the excess NaOH. There, had we done that, in some problems you will find the volume of NaOH and normality is known, and ammonia is allowed to escape, and the amount of excess NaOH is back titrated with a standard acid. So that is simple. Know the amount of excess NaOH and what the amount of NaOH you have taken initially. Then know what is the amount of NaOH consumed by ammonia or ammonium salt, and that is the equivalence of ammonia. That's relatively a simpler analysis, but here the analysis has been little roundabout, little rigorous. What? The ammonia is not allowed to escape out. The ammonia produced is again dissolved in another conical flask containing 300 ml of N by 5 sulfuric acid. So what happens? Ammonia again reacts with sulfuric acid to form ammonium sulfate. This was the sample contained ammonium sulfate. Now also you get ammonium sulfate. The difference is here there was impurity, here is pure ammonium sulfate solution, and we have taken acid in excess. So the excess acid, or the unreacted acid I should say, is now diluted. It's not directly back titrated. It is diluted to 500 ml. And then 20 ml of this solution is equivalent to, 3 parallel lines will indicate equivalent to 15 ml of N by 10 NaOH. This is the back titration. So when we solve the problem, we go from the bottom, from the backward to forward. So first V1N1 is equal to V2N2. Its normality is not known. So once you know the normality, V1N1 is equal to V2N2. Once you know the normality, that normality is the normality of the entire stock solution, 500 ml. Then 500 into that will give you the number of milliequivalents of unreacted acid. Now you know what is the milliequivalents of acid initially taken before ammonia reacted. That will be known from the product of these two. And subtracting whatever excess, whatever unreacted is there, you get the MEQ of sulfuric acid consumed by ammonia. And then by equivalent concept, that is also the milliequivalents of ammonia formed, and that is also the milliequivalent of ammonium sulfate present in this impure sample, because all are metathesis reaction. And then you convert the milliequivalents or equivalents into its mass and then find the percentage of purity. You understood? So the same thing I have done it here before that, and we did together. And this before, ammonium sulfate, excess NaOH, ammonia dissolved in a known volume, a known concentration of acid. The excess acid is diluted to 500. Then the back titration 25 ml is equivalent to this. So go from the bottom to the top. Right? Climb the ladder from the bottom to the top by equivalent concept. Now here is the numerical analysis. The back titration 20 into x is equal to 15 into 0.1. So x is this. That is the normality of the entire stock solution. So the stock solution volume is 500 into this. That will give you the milliequivalents of excess acid, and not excess exactly. It should look like it's unreacted. Right? Milliequivalents of acid initially taken is 300 into 1 by 5. Do you remember that? 300 into 1 by 5. That is 60. So 60 minus 37.5 is 22.5 is the equivalent of the acid consumed by ammonia. So that is also equal to the MEQ of ammonia, and that is also equal to the MEQ of its father, ammonium sulfate. Now you have come to the top. We are interested in ammonium sulfate, not ammonia, not sulfuric acid. So the mass of ammonium sulfate is the number of milliequivalents, kilmilli, and into its equivalent mass. The molecular mass is 132. You will find 2 nitrogen, 8 hydrogen, 1 sulfur, 4 oxygen, 132, and the N factor is 2 here. The total positive charge or the total negative charge is 2 here. So 132 by 2 is the equivalent mass. So we got the amount of pure ammonium sulfate that was present in the sample is 1.485 gram, but the mass of the impure sample was 1.6 gram. So this by this into 100 is 92.8% pure. Understood? This is a very, very simple. I hope you must have developed some interest to solve these kinds of problems. This was a very simple one. When the dilution was done, maybe it would have been simpler, still simpler, had we back titrated, had we taken known volume of NaOH while ammonia was formed. We had allowed ammonia to escape and back titrated, maybe after dilution, the amount of NaOH that remained unreacted. And then we could have got the amount of sodium hydroxide used by ammonium sulfate. So that is the MEQ of ammonium sulfate, right? So when we are going to analyze a mixture, when impurity is there, no name of the impurity, you have to presume that impurity has no chemical role to play. It is inert. But if there are more than one component, that's a mixture you are going to analyze, percentage of each component in the mixture. So there are two possibilities. One, just like impurity, the name of the components are given, out of which, supposing 2 components are there, out of which one is really inert. So it is as good as an impurity. So only difference, there was no mention of its name. Here there is a name that has been mentioned to put you on confusion that if that reacts, what happens? So you have to first finalize whether both the reactants are active or one of them is inert and the other one is active. Let's take this example. 0.5 gram of a mixture of sodium chloride and sodium carbonate were dissolved in water and volume made up to 250 ml. So the stock solution is now 250 ml. And from this, 25 ml of this solution required, this is titration, 50 ml of N by 10 HCl for complete neutralization. Calculate the composition of the original mixture. Now, this is a single titration experiment. So V1N1 is equal to V2N2, 25 into X is equal to 50 into 1 by 10. That is the normality of the entire stock solution. So 250 into that will give you the milliequivalence of, tell me. Now tell me milliequivalence of what? Both? Are both active? See very, very carefully. Are both the components in the mixture active with HCl? No. NaCl does not react with HCl. So this is as good as an impurity, A0. So whatever MEQ that we get, it is the MEQ of the reactant, I mean the active component, that is sodium carbonate. So then you convert to its mass, then find its percentage. The rest of, out of 100, the rest will be the percentage of sodium chloride. Or out of 5, the rest will be the mass of sodium chloride. Now see the calculation. NaCl is A0 here. So the diluted solution V1N1, V2N2, X is coming 0.2, and that is the normality of the entire stock, 250. So 250 into 0.2, that is 50, is the milliequivalent of the hero, I mean the active component, that is sodium carbonate. And mass of sodium carbonate, thus 50 kilmilli into 53. Sodium carbonate is 106, the N factor is 2, 53. So it's coming 2.65. So the percentage of sodium carbonate is 2.65 by the total sample. The impure sample has a mass of 5 into 100, so 53%, and sodium chloride is 5 minus 2.65 is about, not about, 2.35, and the percentage is 100 minus 53, that is 47%. So while you see a problem, you are analyzing a mixture, make sure that both the components are active. Then you have to separately do by algebraic method. If this is X, this is this minus X, and then analyze and add to the total the amount of the product or whatever amount of reactant consumed. So both will be involved in calculation, but in this case only one. See, this is another type of mixture, acid mixture, where you have added 3, 4, 5 multiple acids, 10 ml of 5N nitric acid, 15 ml of 10N HCl, and a certain volume of 9M sulfuric acid. This volume you are asked to determine at the end. Hold on. And certain volume of 9M sulfuric acid were mixed together. And the volume was made up to 2 liters by using a 2 liter flask. Now see, if you simply add, it will be approximately 10 plus 15, 25. Supposing you are adding 100 ml, you don't know. So it will be 200 to 50 or what is like that. But you have to make it 2 liters by using a 2 liter measuring flask. So now this stock solution is 2 liters. And you take, for titration, 25 ml of this diluted acid solution required 35 ml of NaOH for complete neutralization. And that NaOH has the concentration 1.5 gram is present in 5 ml solution. So from that data, you have to find the normality. Or you can do it like this: if 5 ml contains 1.5, then 35 ml contains how much? So if that much, you can convert it to milliequivalent. That many milliequivalents is present in 25 ml of the stock solution. If that many milliequivalents is present in stock solution, then in 2 liters, 2000 milliliters, how much milliequivalents will be present? You can do it in any way you like. That is your jurisdiction. But let's first find out the normality of this. Then we are interested in V1N1, V2N2, right? So the normality of NaOH that is used as a titrant in the titration is equal to the the number of equivalents, NaOH equivalent mass is same as molecular mass by the volume in milliliter into 1000. So whatever that comes, that is coming, I have done it, that is coming this much. So I have not calculated, so it's okay. So let it be like that. Then V1N1 is equal to V2N2. 25 milliliter of the acid solution, the mixture of acids. 25 into X. That X is the normality of acid, the acid mixture present in the stock solution, 2 liter solution. So 25 into X is equal to 35 into this, whatever you get. So here we get X is equal to, let me show you, X you are getting 10.5 N. So that is the normality of the mixture, the stock solution. Normality of acid means normality of H plus ion. So you remember that one equivalent of acid means it contains Avogadro's 1 mole of H plus ions, not loss and gain of electrons. So the normality that you got for the entire mixture is 10.5. That means 10.5 equivalents of H plus ions are present in per liter of the solution. So hence the normality of H plus ion in the entire 2 liter solution is 10.5. So use the volume of the stock solution 2000 into 10.5. 21,000 is the number of milliequivalents of H plus ion, right? So, and what is the total volume of the solution originally you have taken? 10 plus 15. Supposing this volume is X that you are asked, X. So 15 and then I'm sorry, then you just find out not volume, the total milliequivalents of H plus ions in all the three. 10 into 5, 50. 15 into 10, 150. And if the sulfuric acid volume is X, the 9 into 2, because molarity has to be converted to normality, the n factor is 2 here, so 9m is same as 18 normal. So 18 into X, the volume is not known. So this is the total number of milliequivalents from the 3 acids. Total number of milliequivalents of H plus ions from the 3 acids. And we already have got from the titration experiment 21,000 is the number of milliequivalents of H plus present in the stock solution, 2000. So if you equate this, one data from the individual acids where unknown X is there and the other from the titration, then you are getting X is equal to 1155.555 milliliters, so 1.155 liters. So in the original mixing time, you have taken 1.155 liters of 9m sulfuric acid along with 10 ml of this, 15 ml of this. So the total volume would have been 1.155 plus 0.01 liter, 0.015 liter. So this is close to 1.2, something like that, 1 point. And you have added the excess with distilled water to make the volume equal to 2 liters, and then perform the titration experiment to know the normality of H plus ion. So in this question you are asked to find what is the volume of the original sulfuric acid mixed with these many milliliters of this, these many milliliters of this. Got it? Here there is no reaction, simply dilution. Only you had to convert it to a normality, because you are finding out the total equivalents of H plus ions. The normality of the mixed acid means it is the normality of H plus ions, right? Number of equivalents of H plus ions per liter. Now We have three types of titrations. We already know that. One is the acid-base titration, as we call acidometry, alkalimetry. The other one is redox titration. You already know that. So let us solve a problem from redox reaction. A straight problem from redox reaction using V1N1, V2N2 normality method. We can also solve by molarity method, converting molarity into normality. That we know. Now, what volume of M by 25 potassium permanganate is required to oxidize 30 ml of M by 10 ferrous sulfate in dilute sulfuric acid medium? What mass of KMnO4 present in that volume? So it is a simple titration, a redox titration. You know the volume, you know the concentration, you convert into molarity. Ferrous sulfate will be oxidized to ferric sulfate. The N factor will be 1. So M by 10 is same as N by 10. But KMnO4 in acidic medium will have an N factor of 5. Manganese will go from +7 to +2. The change is 5. The N factor is 5. So M by 25 is 5 by 25 N. 1 by 25 into 5. That is 5 by 25. That is 1 by 5 N. So once you know the normality, the V1N1 is equal to V2N2 is there, is readily available. So you have done this problem. I have done this 20, not this one. Let us do it together. I have not done. So this is very simple. Say volume, say X into 1 by 25 into the X factor is 5 for potassium permanganate, and here it is 30 into the X factor is N factor is 1, so 1 by 10. So here we get X, this will be how much? This will be 3 into 5 is 15 milliequivalents. So that is the normality, 15 N. I'm sorry, 15 milliliters. I'm so sorry. Now, instead of doing that, if we so it is asking what mass of KMnO4 is present in that volume. That means 15 ml. So since we have already done, then MEQ of KMnO4 is equal to 15 ml into 1 by 5. That is normality. So that is 3 MEQs. So what is the mass? Mass 3 by 1000 into, and the molecular mass is 158 and the N factor is 5, so it's 31.6. so whatever it will come, that much amount is present in the given volume. So what volume of M by 25 KMnO4 is required? First we got this 15 ml. This is one answer. And then it is asking what mass of KMnO4 is present in that volume. So you have to convert it to amount. The volume multiplied by normality will give you the amount in equivalents or milliequivalents. This is milliequivalents because it is milliliter. Then you convert it to its mass by using equivalent mass and killing milli. Got it? It's very simple. Now this is another problem, and I'm sure that we are almost at the last part of our program. It is I think it is almost 1 hour. We can stop here and go for another session if it is possible. But I think to complete, I will take a bit of speed, but I want like to have another session of similar types of problems. Now see, 1.5 gram taking speed, 1.5 gram of a saturated solution of oxalic acid, crystal, formula is this, it is a dihydrate, were diluted to 100 ml, and 20 ml of this stock solution required 27 ml of N by 10 potassium dichromate for complete reaction. Find the solubility of oxalic acid crystal in water in gram per 100 gram of water. In gram per 100 gram of water. Now let's go for the titration. 20 into x is equal to 27 into 1 by 10. Here the normality is given. Had there been molarity, then the n factor would have been taken to convert molarity into normality. Here the n factor would have been 6. Doesn't matter. Normality is given. So you are getting normality of this diluted oxalic acid solution is 0.135 n. So oxalic acid number of milliequivalents is the volume of stock solution into the normality, 13.5. So what is the mass of oxalic acid? 13.5 by 1000, and oxalic acid crystal, you have to take 2 water also. 90 plus 36 by the n factor is this is a reductant where the number of electrons lost is 2, and that is the change in oxidation number is 2. So by 2, that is the equivalent mass of the crystal. So you get the mass 0.85 gram. So that is present in 1.5 gram of the solution. So what is the mass of solvent present there? So it is 0.65 gram. So what is the solubility per 100 gram of water solvent? So 0.85 divided by the mass of the solvent into 100. So in 100 gram, 130.7 gram of oxalic acid crystal is there. Can you believe it? The solvent is 100, but the solute is of greater amount than the solvent. Doesn't matter. It can mix thoroughly to form a concentrated solution, and that's a saturated solution, and its densities will be quite larger than that pure water. Forget about that. Had it had been asked what is the W by W percent of that solution, then you would have said 0.85 by 1.5 into 100. Mass of the compound by mass of the solution into 100. But it is asking solubility per 100 gram of water. That's why we have to subtract and got the mass of water. Now what is iodometry and iodometry? I think I stop it here for a better clarity so that you take rest. So we will take up iodometry, and some precipitation titration along with that's the end. Of course, let us finish. It will be 1 hour 10-15 minutes. Let us please bear with me, please. Now iodometry is the reaction in which iodine is produced. In sample analysis, and some oxidants are allowed to react with excess Ki to produce iodine, and that iodine is estimated by iodometry. Iodometry is the process in which iodine is consumed. The process in which iodine is produced can be of many possibilities. Supposing you are analyzing a copper sulfate sample, you can treat it with excess Ki to produce its equivalent quantity of iodine. So here there was a misconception earlier that cuprous iodide has a formula of Cu2I2. When I was a student, I was told like this, but no evidence that it is remaining in a dimeric form, Cui. It's not like mercurous. So we were told by our teachers that it is in dimeric form, Cu2I2. But now it is known that there is no evidence that it is forming a dimer, so Cui. Similarly, if you are analyzing a sample of hydrogen peroxide, you can treat it with a Ki to get iodine. Supposing you are handling potassium bromate, you can treat it with Ki to get iodine. So the formation of iodine is called iodometry. Once iodine is formed, you can estimate that by titrating with the titrant sodium thiosulfate, sometimes called hypo solution, is used in photography. But hypo is a hydrated crystal containing 5 molecules of water per unit of sodium thiosulfate. But sodium thiosulfate is Na2H2O3, and the famous reaction it gives sodium tetrathionate and sodium iodide. So this is the titration experiment, the back titration experiment. Sodium thiosulfate is kept in the burette as a titrant, and iodine produced is titrated, and towards the end of the titration you add the indicator. Starch is used as the indicator. The moment you add starch solution, the entire solution containing iodine becomes blue. It forms a blue complex, blue, and you go on adding sodium thiosulfate in a dropwise manner till the end point where the blue color of the complex, the iodine complex, will vanish. That's the end point to know how much of the titrant, that is sodium thiosulfate, is consumed, right? Now by that, let me concretely discuss with you a problem relating to iodometry and iodometry, right? So the problem says like this. I am taking speed with your consent. 50, you also have to focus more. 50 ml of an aqueous solution of hydrogen peroxide was treated with excess Ki. 50 ml of aqueous solution of H2O2 was treated with excess Ki in presence of some acid. That's a catalyst. The liberated iodine required 20 ml of 0.1 N sodium thiosulfate solution for complete reaction, not neutralization here. This is the redox reaction. Calculate the concentration of H2O2 in gram per liter. In gram per liter. So let us go from the back titration. So what is the milliequivalence of sodium thiosulfate that has reacted with the iodine produced? So 20 into 0.1. 20 into 0.1 is 2. So the number of milliequivalents of sodium thiosulfate is 2. So that is also the number of milliequivalents of iodine present in that solution. Now I would ask you to convert into millimoles, because we are climbing the ladder in terms of mole now. We cannot run a risk of going in terms of equivalents. So immediately I converted this number of milliequivalents of iodine present in that solution into its millimoles. The N factor is 2. Iodine for 1 atom, 1 electron, 2 atoms, 2 electrons. So 2 divided by the N factor is 2. So 1 millimole. So then I wrote the equation, the first reaction, I wrote the equation and balanced it. H2O2 plus 2 Ki, this I2. Here also I find 1-1 relationship between the reactant and the product. If 1-1, then it is already 1. 1-1. So 1 millimole of iodine will be produced by 1 millimole of H2O2. So the mass of H2O2 is equal to 1 kilomilli into the equivalent mass of hydrogen peroxide is molecular mass of hydrogen peroxide. Here is millimole. So molecular mass of hydrogen peroxide is 34. It is 0.034 gram. And if 50 ml solution contains this much gram, then 1000 ml solution will contain how much? It is, the concentration is 0.68 gram per liter. But we could have gone by the equivalent method. Had we just imagined, made sure that iodine has the same N factor in both the reactions, then we could have climbed the ladder by equivalent method. See here. Since the N factor of iodine remained the same in both the reaction, in the back titration, this one, the N factor is 2, and in the production of I2, here also the N factor is 2. So there are 2 Ki, 2 iodine. So for 1 iodine the change is 1, 2 iodine change is 2. So you could climb 2 H2O2 to the top by equivalent concept here. So the number of milliequivalents of iodine is 2, the number of milliequivalents of H2O2 is also 2. So to get the mass 2 by the by 1000 into the equivalent mass, which is 34 by the n factor of H2O2 is 2. The total change in oxidation number is 2 here in this. So the n factor of H2O2 is 2. That is 17 here. So you got the same answer. The same quantity of H2O2 is present in 50 ml. So in 1000 ml, how much? You get the same answer. But I again caution you, don't do it by this method, because for this you can use equivalent concept, because iodine is produced here with n factor 2 and iodine is consumed in iodometry with the n factor 2. So you can well use the equivalent concept, but no. Now this is the last part. Precipitation titration also can be handled by using a selected indicator, as you know. So look to this problem. 5 point, I'm taking speed because this is the last part. No, this is not the last part. So no, I would like to take a break here, and boys and girls, ladies and gentlemen, I will not further put you into any monotony. I break here after iodometry and iodometry. Just let me revise. The process in which iodine is produced is iodometry, and the process in which it is consumed is iodometry, and that's the titration. The only one titrant, that is sodium thiosulfate, is used for that. But there are multiple methods by which iodine is produced, depending on what sample you are analyzing. Right? If you are analyzing an oxidant sample, you can use a Ki to produce I2 in all the cases, in most cases. Right? So with this we conclude, and in the next video, I think after some time, I will take a break and I will make a video for you where I will be doing for precipitation, and also for I will solve a problem where I will show that you must not climb the ladder by equivalent method. I will caution you by solving another problem in your presence, right? So then we go for the situation where you will have to use two acid-base indicators successively or separately. That I thought to include in the last part, but this will be having some revision of this. This is almost a revision of, almost we have completed the summit part. The Kilimanjaro summit is almost complete. That will be 100% complete when we learn the problem involving double indicators, right? So we are almost at the threshold of the mount top. Which mount? Kilimanjaro, where it is present in Tanzania, right? So with this, bye bye, see you soon. Have you subscribed to my channel? If not, what prevents you? If you are now attached to my videos, so please make sure that you have already subscribed. It feels better for you and me. And also you have liked this particular video. Click on the like sign. Bye bye.